high energy particle physics. And this year we're scheduled for another visit by Dr. Feynman. And I think probably without further ado, Dr. Feynman.
It's a characteristic of universities that they change the students from year to year. And that's characteristic of the professors, that they don't change at all. And so my natural inclination is to continue with this series of talks that I've been giving for the last 4 years with the new one. But I realize it doesn't going to work. So what I'm going to do is go back over the 4 years and give very brief summaries of the things that I said on other talks, with the result of, and then tell you if I have time, of anything new. Actually, it's kind of fun because it's only 4 years and there's been quite a change. When I went over the talks, I see the viewpoints shifting as we go along. So it makes a nice story. There's too much to high energy physics, and so I limited it partly. There's weak interactions and strong interactions. Of course, there's electrodynamics also. And all I'm going to talk about is the strong interaction. In case you fall asleep during the lecture, the final result is that we think we have a theory and there's some evidence that it's working for the strong interaction. All right? Now I'll give the lecture. It begins with the particles that interact strongly, that, of course, that come from the nucleus, starting with a proton and neutron. And when these I got this upside down. Let's see. Yes. When these are investigated, -1. Really, yes, that's right. I was going to say it's I, but that's 90 degrees. You start with a neutron and proton, and when we investigate them and hit them together and so forth, we found thousands of different hundreds, 400 different states. But typically, they discovered that they went in multiplets, and they were classifiable in two groups called baryons and mesons. And the neutron and proton are here. I have here measured the mass. And then we find objects appear to have characteristics of different kinds of quantum numbers of charges and isospin and so on, and strangeness, which I won't go into. But we're able to make a table in which we put the charge horizontally and the mass vertically and find the objects coming in multiplets. This is the lowest energy multiplet of baryons of spin a half. Not only is there a neutron and proton, a lambda, 3 kinds of sigmas, and 2 kinds of C's. By the way, there are so many particles we ran out of letters, so we call other particles by the same letters. We have to remember which C you're talking about by giving the mass. That's why I can remember all those numbers. In addition, there are mesons, which are different than baryons. They are common pi's, for example, and k's and etas is the slowest multiplet, for instance, a multiple of spin 0. As you go to higher energy, they find more multiplets of all kinds of spins. And the next multiplet, for instance, I got it organized here. That isn't going to work. Now let's see. We'll do it this way. If I'm not organized at the beginning, it'll be chaos at the end. Okay, now here's another multiplet of the same idea of a little higher energy. It's the baryon with spin 3 halves. And mesons of spin 1, for example. The baryon, this multiplet shows a symmetry, a pattern, which is more obvious than the pattern that you could see on the other multiplet. That's why I bring it out. All I had to do is say, to summarize, there's lots of multiplets. But it's kind of fun that there's a pattern. All these particles have nearly the same mass at 1236 plus or minus 1 or 2. And the charges go -1, 0, +1, and +2. At a higher energy, a mass of 1386, and carrying another quantum number, which we call strangeness, which makes it also different, but in this purpose, the mass is enough. There are 3 particles of the same mass, but they only go -0 and plus, and they don't have a double plus. And then at a still higher energy, there's another thing, particles of spin 3 halves, minus and 0, no plus. And they carry 2 units of this other quantum number called strangeness. And finally, it was predicted after we saw that much, that the next state would exist, which have a higher index on the strangeness number and would consist only of a minus particle, and its mass would be around there because it was observed that the differences in mass were all about the same. In the case of mesons of spin 1, we have rho mesons that come in 3 varieties, plus, minus, and 0, and also an omega meson, which comes in only 1 variety, neutral. It's almost the same mass as the rho. They're very close together. Then we have things called K stars, and they come in minus and naught, and they're antiparticles. Every particle has an antiparticle and always has exactly the same mass and other properties that you can get by reflecting signs. For instance, the antiparticle of K naught is a K naught star. It has also to be neutral. The antiparticle of the K minus would be K plus, which is called K plus. And mass is all the same, so there really are 2 particles at that level. The strangeness which can be measured is -1 for these and +1 for those 2. And then there's a phi particle at 1020, and that's that multiplet. And then higher up, there are more multiplets. All right, now the thing is, and I told you about all this on the first lecture that I gave here, and went on to discuss the theory of it, which was developed, which was called the quark theory. It was that there are little elements called quarks out of which these things are made. And the quarks come in 3 varieties, which are called U, D, and S type. And the electric charges of the D and S are the same, -1/3, while the U has +2/3. When you have a quark of an S type inside of something, it's supposed to have, it explains this quantum number of -1, this strangeness number. Also, it gives mass to the multiplet. It's all empirical. A way of speaking would be to say that the S has more mass than the D and the U, and the D and U have both about the same mass. So whether it's a D or a U doesn't make any difference with regard to mass. Obviously, it makes a difference with regard to charge. Each of these quarks, of course, come as an antiparticle also, an antiquark, which have bars on the top to represent them, and the charges are reversed, and so is the strangeness number. These objects have spin 1/2. And the idea is that the baryons are to be made by putting 3 quarks together. The mesons are to be made by putting a quark and an antiquark together. Those rules explain all the magic of the multiplet. And to take the single illustration that I had, I'd like to explain one multiplet. The multiplet corresponding here, it's a baryon, so it should be representable as a quark, as 3 quarks. So we find out what can we do by putting 3 quarks of the kind we just mentioned together. Well, if we put 3 quarks together, we can do different kinds of combinations. This represents the 3 quarks, and by the way, in this particular multiplet, all the 3 spins are exactly parallel, though the total spin is 3 halves, so we check that out all right. And we can make different kinds of things depending upon a mixture of whether it's an S's, D's, or U's that you put together. Start down here, for instance, if we have D's, all 3 D's, the charge would be -1 because of -1/3 times 3. That's easy. If you change a D to a U, you increase the charge by 1 unit, or else you can figure it out from the beginning again, -2/3 and 1 + 1, 2/3. This is 2/3, you remember, that's -1/3 each D. So it adds up to 0. And then if you put 2 U's and a D, you get +1, and 3 U's, each being 2/3, gives +2. And all these masses are about equal. So far, so good. Now, if we add an S type instead of a D type, we replace one of the D's by an S. Then we get SDD, SDU, and SUU as the only possibilities with 1 S. And that corresponds to what we call strangeness -1. And has a higher mass because it contains an S and has only 3 possibilities. Then if you put 2 S's in, it has still higher mass and only 2 possibilities. And finally, you can put all 3 S's and get a charge of -1. And that's as far as you can go, and that multiplet is neatly explained. The other multiplet that I showed you with the neutron and proton is more complicated, but also explained, and I explained it in the first lecture, which we will forget now. But it has to do with the fact that the spin is 1/2, and there's some kind of symmetries about the up and down spins, and I don't want to go into that because I haven't got time to give the first lecture over again, only to illustrate how things were going. In the case of the mesons of spin 1, which are made by putting a quark and an antiquark together, both spins parallel, you can make things by putting, obviously, same game, taking different combinations and making 9 combinations of the 3 quarks and the 3 antiquarks. And the 9 combinations come out nicely with the charges and everything, with the right strangenesses, etc., as indicated by this, which just takes a minute. For example, the phi is SS bar, very heavy, the heaviest one, because it has the S quarks, which makes it heavy. The ones that are lightest don't have S quarks, and those are the rho, which come in the du bar and the ud bar, and a combination of dd bar and uu bar. The omega is another combination of dd bar and uu bar. You say, which is which? It's a feature of quantum mechanics when the two levels are degenerate, that the state is sometimes neither one nor the other that you expect, but some linear combinations. And in this particular case, the rho naught is the linear combination of uu bar and dd bar with a minus sign between them, out of phase, while the d omega is the two states in phase, and it's split that way rather than making it easy for me to explain that the rho is uu bar and the omega is dd bar. Not quite, but almost, okay? Now, I told you that there were hundreds of multiplets, and you've only seen me produce two, and you wonder where they come. Well, you can have one change by flipping around the way the spins go. The pions are like the rhos, except that the spins are not this is confusing. The spins are not parallel, but opposite, and the proton and neutron have got the spin arrangement of a half total instead of 3 halves. And that takes care of that, but there are still more multiplets, and those we understand, we think, by supposing that the quarks that are inside have dynamic motion. Just like a hydrogen atom in the lowest state is an electron and a proton with a certain kind of spin orientation, and you can flip the spin over. It's called a hyperfine splitting of the ground state. So also it's possible to excite the hydrogen atom to higher states, which have the same elements inside, a proton and an electron, but they have dynamic angular momentum, for example, and so on. And when you put that idea in, then imagine that these quarks can move around each other with angular momentum other than the first states, which I just showed you, which are, they're all sitting on top of each other. It's called an S state with no angular momentum. And you add that, then you can understand the pattern of the higher multiplets qualitatively, all right? And that's the way the theory goes. All right, now to continue the report. Now this is new and is, different than was on the first lecture and was not available 4 years ago. There was an interesting experiment by which you can make the mesons of spin 1, which are the ones I showed, which are neutral. That, to remind you, is the omega naught, the rho naught, and the phi. Or not the ones without strangeness also. And the way it's doing is to hit 2 electrons together, because 2 electrons can come together. They turn into a photon first, and that turns into the rho. But damn the details. You can make hadrons. And the probability of making hadrons varies with the energy. And here's a plot of the probability of making hadrons as a function of the energy of the beams, of the total energy of the 2 beams of electron and positron. I don't know how to do anything up here, so somebody else will have to figure that out. Yeah, that would help a lot, wouldn't it? As a function of energy, you see that the probability of producing hadrons rises very, very sharply to what we call a resonance when the energy of the beam is just right to make these particles. These particles actually decay into others of lower energy, such that like the rho goes into 2 pi. And so they have a little width. So this is not exactly a delta function. You don't have to have the energy exact, but you see it rises to a resonance and comes down as you vary the energy. And there is the resonance, which on this scale, you can't distinguish the position of the rho and the omega, although that can be expanded. And then a little higher, at about a million, it was 1020 if you remember any of the numbers, which I doubt, you get this phi meson, which is the SS bar combination. This was the UU bar and the DD bar. And then there was a tremendous excitement some 3 or so years ago that as they went up in energy, they found another tremendous resonance where they didn't expect it, and which the quark theory would be completely incapable of understanding. If this were to be made of U's and D's in some complicated combination, or U, D's, and S's, there's no reason why it shouldn't come apart extremely rapidly into other hadrons and therefore have a very wide width, but it was extremely narrow. You will notice another one higher up, which I'll mention in a moment. Also notice that the energy only goes up to 8 here, okay? And further, that up to that energy, although there's lots of wiggles, there's no other indication of another one of these wonderful super resonances. Well, this psi particle, people are still debating whether to call it a psi or a J. It's a contest because it was discovered independently at the same time by another experiment. By hitting protons on nuclei, it was possible, and looking for pairs of muons, it was noticed that if you calculated the mass of object that the pairs of muons came from, a especially large number of them came from a mass of 3.1. And that meant there must be some particle which disintegrates into 2 muons at 3.1, same particle. And those guys called it a J, but the electron people called it a psi. And it's been that way ever since, unfortunately. I'm going to call it a psi because I like the electron experiment better, okay? Prejudice, pure prejudice. Now, since that time, we would expect that if this, what is it? We have to say what it is. And what it is proposed is, I meant to be able to, sorry, you can't see that one. It can't be explained the way with these quarks. There was already from weak interaction theory an expectation or an argument that there ought maybe be another quark of higher mass, and that there's another object up here, and if I had my pens, which I haven't got, I could mark it, but I'll put my finger there, and you'll understand. We'll call it C quark, C. It has a charge of plus 2/3, and it has a mass which is much higher. I mean, it contributes more mass to states. If we put it up here, we now have 4 possible kinds of quarks. Those kinds are now called flavors. So the quark can have 4 flavors. It can be a U flavor, D flavor, S flavor, and C flavor. And the thing that we've been looking at was the CC bar combination, which on our original plot with the phi, there would be a higher one at CC bar. Now, since that time, just to impress you with progress of experimental nature, the whole structure of this CC bar system has been, not the whole structure, has been analyzed. This is the original state which was discovered, but the CC bar will also go around each other, producing not only S states, but P states, theoretically, and here are 3 states which have the right angular momentum to be what you'd get from the P state excitation of this. This is the other state up here, is a state which would be represented by a second radial node. That's also an S state, but higher up. And that was what that second peak was, that psi prime that was on there. It's not a new quark. It's the same pair of quarks, but with a radial node in the wave function, as we interpret it at any rate. These states, with the dotted lines only means they're not so well understood as the others, correspond to other combinations of the spin, opposite instead of parallel. And this state is a D state with the spin so arranged that the total angular momentum is 1, and so on. All these transitions which you see marked here indicating the relative probabilities of gamma ray emissions and hadron emissions and so on, all experimental discoveries. So since the discovery of the psi, it's got to be a very common object. It's just like an atom. It's got lots of levels, it's got transitions, it's got the whole, every time we do physics, we see the same physics. You know, it's all the same. The only reason is that that's the only part we can understand, that we make progress with, is the part we've seen before. Okay? Then that was just to impress you with progress. But if quarks have possibility of being a C, then if we consider, for instance, just the example of mesons, of a quark and an antiquark, before we found that with this quark and this antiquark 9 possibilities, and I discussed them. We now have with this and its antiquark C bar, 1 kind of state, the psi's with CC bar. But we ought to have other states such as C U bar, or C D bar, or C S bar, or the antiparticles of those, which would be SC bar and so on. But the antiparticles always come, we always know we're going to get one. So people have looked for particles which contain this C quark, sometimes called charm, horrible name, alone with another kind, not the C and anti-C, so that the charminess would not cancel out because the anti-C is, so sometimes that's called naked charm, which bothers me still more. At any rate, to show the progress, we now have discovered particles corresponding to those expected states from the same theory. Here are the states interpreted, they've been discovered, interpreted as C U bar. They are neutral. If you change a U to a D, so you get C D bar, you get particles of almost exactly the same energy. The differences in energy are indicated and measured here, and they're only in the MeV region, where these things have a total energy of 2,000 MeV. So there they are, and here is an excited, this is the one of spin 1, and this is the one of spin 0. They're both S states. It's as much as we've seen. There's a lot of stuff up here somewhere else, but we haven't got there yet, okay? And these have been discovered, and then for a while, those We waited, took a while, a year to find those, and then there was a delay where the other Fs, which we expect was CS bar, and in Hamburg they found the Fs. And we don't have as much information about that, but they're up at this mass, the one of spin 1 and this one of spin 0, and they're positively charged. Okay? So we have all the combinations of the mesons, at least, with the C quarks and the ordinary quarks that we knew and loved so much before. So the idea that the quarks come in 4 flavor varieties is confirmed very nicely. There are some evidence of hadron-like things which contain 3 quarks, one of which is a C type, but there's not as much data. I'm short on time in this talk. I think it can go on forever, but there's a little bit of evidence. Nothing so beautiful as this with so many states and measurements with precision of the energy, but there is evidence that definite evidence that definitely those states exist, and that some of the masses have already been measured, about 2 or 3. Things like a C quark, a U quark, and a D quark state, for instance, has been found. Well, unfortunately, we don't see any more. Now, once you see 4 quarks, 4 flavors, you say, well, maybe there's more flavors. That type of intelligence is available to us all. And so you hunt for them, and you look on that, and you saw that curve that showed no more bumps. The reason to have made that curve so carefully was to look for more bumps. Nobody found any. But then they did the other experiment with protons, looking for pairs of mu's and going out further and further, because in the proton beams there was more energy available than in this electron-positron experiment. So although the electron-positron experiment gives much better precision in the end with possibilities of measuring spectra, etc., the other one shows the existence. Here's the curve of the pairs of muons that are produced as a function of the energy, or the mass really, that had to disintegrate to make that pair of muons. And you find as the number that you get goes down, 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 down smoothly. And when you come to 9 something or 10 in that region, it rises in a little bump and there's a little side bump. It looks like there's more states. This is the way the psi, or J, was discovered, so this will be the K. And if its interpretation is right, but we have no more experiment than just this, it could be interpreted by supposing there's still a 5th flavor for quarks, which has already been named ahead of time, because people are always inventing. As soon as somebody sees 4, guys immediately put out papers explaining why there ought to be 6. Nobody put out a paper for 5 because 6 is a more symmetrical number than 5. The reason for putting out such papers is, of course, so that you get your name on it quickly if it does turn out to be 6. So then they will also, you name them. And they've been named top and bottom. I don't like the idea of naked bottom, but never mind. Anyway, if we call the new type of quark T, without saying what it is, then these states would be interpretable as a TT bar state. This might be TT bar, this BB bar, or this might be TT bar, and more likely TT bar excited, just like the psi and psi prime. That's still to be seen, okay? We've got the bumps. We have no other interpretation. The guess is that there's at least 5 flavors, and therefore 6, at least, because 5 is a kind of a number that's all. That's the whole theory, that 5 is a funny number. So therefore, when you see that, you deduce the existence of 2 more quarks, just because 5 is a funny number. All right, that's the position of the quark theory of hadrons, plus all the wonderful new hadrons with charm, and now possibly with topity. Topness. Okay, now that was 1 year plus modifications for new flavors that came after that. The second year, I told you about evident experiments trying to see if the quarks are really inside the proton, not just they give the right energies to the states and the magnetic moments approximately right, but can you see them in there? And so the picture, it was done by an electron-proton scattering, which I described in the next lecture. Since I cannot see a clock, you're at my mercy. I don't know how long it's taking me. Okay, a very fast proton moving in the center of mass was supposed to hit a proton standing still was hit by an electron. But we think in relativity in the center of mass, a proton hitting an electron. And the energies were so high, they did an experiment in which they hit a proton with an electron and measured the energy of the electrons bouncing off and how many came at different energies. And if the proton, we argued theoretically that a proton moving along could be thought of as having constituent parts, quarks, and perhaps something else, which was called gluons, because one of the problems is what holds the quarks together inside the proton. Oh, thank you. Yes, you don't want to be at my mercy. Good. That's fine. You can't read it. So the picture was that just like electrons and protons are held together in the theory of quantum electrodynamics by the exchange of a photon, it was imagined that whatever it is that holds it together is the exchange of something, and it had to have a name. So we were very good at names. We called it a gluon, the glue that holds the quarks together. So there might be some gluons in the proton also, and the proton going along then could be represented by the fast-moving proton as a bunch of fast-moving quarks and some gluons. And so they would be going along this way, and it's represented in this picture here. And the idea was, there was a principle of scaling was proposed by sort of guessing, but there were some good arguments, that the probability of finding a quark of a given momentum inside, which is a certain fraction x of the momentum of the proton, would be a function only of x. The probability of finding quarks with less than 1/3 the momentum of the proton is the same whether the proton is moving at 10 GeV or 100 GeV, all right? That's the idea. That's called scaling. Also, because all the objects in there don't have to be standing still, they're moving this way. As they go along, they have transverse momentum, but relativity makes it so any motion this way, when you transform it, stays and doesn't build up. So the guess was that the transverse momentum kicked up and down here would be limited and would be independent of the momentum p. And with those two principles, we were able to analyze the electron-proton scattering by considering that what really is happening is that the electron is hitting the quarks inside. And so by measuring how much energy the electrons lose, you find out how fast the quarks are moving inside. It's the kind of conservation of energy business. And so by measuring the electron distribution, you could determine the distribution of momentum of the quarks inside the proton. So that made them observable. But the question is, if so, you see an answer and you interpret it as the momentum of the quarks. How do you know it's right? Well, first, you get the same distribution independent of the energy of the experiment. Good. And second, you have some more definite check that it's really quarks and not some any old charged things inside. You're using neutrinos to do the same experiment and electrons, and knowing electrons are coupled proportional to the charge, but neutrinos are coupled to the quarks the same way, we can measure by the ratio what the charges are of the quarks. The probability of scattering comes out proportional to the square of the charge of the quark. And so if you would scatter from a proton, you would get the mean of the square of the charge of the things from which the electron was scattered. It was hard to do it with neutrinos on just protons. You have to do it on iron because you have to have enough stuff for neutrinos. And so it was an average of protons and neutrons, okay? So they had the same number of D and U quarks. If you don't remember, oh, I never told you, but a proton is 2 U's and a D, and a neutron is 2 D's and a U. So iron is mostly the same number of D's and U's. And the average charge then would theoretically be 1/9 plus 4/9. That's a 1/3 minus a third squared and 2/3 squared. Average is 5/18, which is close to 0.27, and the experiment was 0.27 plus or minus 0.05, I think, which was very good. So that checked that the charges are right, and it was a dramatic experiment. It also is to be pointed out that from the electron experiment, also neutrinos, you're only measuring the quarks. The electrons don't scatter from the gluons, which are supposedly neutral. They just carry momentum back and forth. And therefore, the total momentum of the quarks would not add up to 100% of the momentum of the proton, and it doesn't. You're lacking about 50% of the momentum, so there is definitely momentum in gluons. There must be another element in the system, gluons. Okay? But gluons haven't any flavors or anything and do not alter all those quantum numbers and everything else. They're just the force which holds the quarks together. That's lecture 2. Now, the third year I came around here and I discussed the question, third year, maybe if I look close. Oh, not so bad for the third year. What happens when there was an enormous amount of experiment hitting protons on protons. That's hadron-hadron experiments. They're much harder to interpret because, you see, with an electron hitting a hadron, at least half the thing is understood. The theory of electrons is complete at the present time. The theory of quantum electrodynamics shows so far no errors, and we now understand the electron and the photon at the moment. But the hadron, we don't. So an electron-proton scattering is half understood already. We understand the electron, and we use it, the tool, to learn something about the hadron. But with hadron-hadron experiments, you hit two unknowns together, and you get a lot of unknowns out. The picture then is that in a hadron-hadron collision, we try the same view that really the protons coming in here to collide are just the same quarks and gluon mixtures with a mixture determined by the electron experiment, with a distribution determined by the electron experiment. And then quarks hit each other by some law, presumably by the exchange of a gluon according to that theory, just like two electrons exchange a photon. And if that were true, that would be the way the picture would go. There's that gluon exchange inside that little green spot that you could probably see. And we tried to interpret that. First, if I forgot to mention something important, which is obvious. If quarks were to come out here, we'd see quarks in the experiment outside. No quark has ever been seen outside. Free. That is, the objects of charge a third have not directly been observed. Otherwise, it would be easy. Nature made it hard for us. We got to discover the quarks without being able to take it apart. The picture now is that when the quarks, in this view, the idea was that when the quarks come apart, a force which gradually rises with distance does not permit them to come apart. This force grows until the field gets so big that pairs are produced, pairs of quarks, and they combine together in these little lumps of quark, quark, anti-quark, and so on, making hadrons. So all we ever see are hadrons of never free quarks. It's an invention to explain the lack of observation. So with that kind of qualitative theory, and plus a certain amount of quantitative theory in here, we would try to tell whether that's true. If this theory were right in that simple picture, if I were to change the momenta of the incoming protons here, say that's a very large number, say it's p, and I change it, say, by a factor, say I change it to 2p, then the theory of the exchange of gluons tells us how this cross-section changes with energy. And it turns out that if this factor I call E, then the cross-section of this part would go as e to the minus 4. And therefore, the apparent cross-section in this experiment would also go as e to the minus 4, because we assumed that as we change the momentum of these, because of scaling, the probability of finding quarks are all in proportion, everything's in proportion. And therefore, we would get e to the minus 4. It's true that I'll mention something now which I ought to mention later, but it doesn't make any difference. There's a little complication because there is a little sideways momentum in there. So when you observe a particle out here with a given transverse, we call it transverse to the beam, or perpendicular momentum, the momentum you observe is not necessarily the momentum that was given just to the quark, because the incoming ones may have had some of that had originally some of that momentum, you see. So you find one of 2 GeV doesn't mean that the quarks that came knocked sideways 2 GeV. They may have each had a half themselves, only one. There's a complication. Insofar as that's true, the scaling wouldn't work. But with the sizes of the perpendicular momentum, which we thought were allowable, the energies were high enough that we would have expected this to work, this theorem. The energies, it would only work with high enough energy. And we thought the energy was high enough. But when we did the experiment, we discovered that the results go more like energy to the minus 8. And I'll illustrate that. Experiment this way. Here is an experiment of a cross-section which is supposed to go as e to the minus 4, according to p perpendicular, some momentum to the minus 4, if the theory were right, but we multiplied by momentum to the 8th, which is much different. And here's a scale of things. It changes from 2 to 4, 8. You see, it's a big factor to the 4th power. So we use the 8th power, then it gets flat. Then the cross-section's independent of energy. This is another way of saying that the cross-section's falling as the 8th power. That's a way of demonstrating that. Also, the quantum chromodynamic theory, the theory of gluons and quarks, which we were trying to discuss, had been developed in much more detail, and I'm going to tell you about it in a moment. But I'm trying to get to where it was last year. It had been developed last year, but it wasn't working because of this. It also didn't work because the size of the cross-section that was determined by that theory said that it should be much smaller than experiment. Our experiment was too big and falling too fast. I mentioned at that time when I gave the lecture, it's always possible that it falls too fast and then it comes in right, and then the theory is okay. See, experiments too big and falling too fast from the theory. Well, it's always possible. If you went to higher momentum, the theory comes out right. But you still would have to explain what was wrong with the lower momentum. Therefore, what we had done previously for an empirical analysis of all this stuff was to give up on this theory that said it was e to the -4, this gluon exchange theory, temporarily at least, to see what happened, and assume that there's a new law of quark-quark interaction, which for some mysterious reason goes as energy to the -8, and then see what happened. And of course, we could, with that fixing up, we could fix up everything, and everything looked good, except there was a few little things wrong. The major difficulty, oh, I forgot to bring the slides. Well, we'll just tell you that in an experiment in which two protons come together, the experiments got more elaborate. They had counters on both sides, and they would have one counter go off, which is called a trigger counter, with a particle coming into it, and then they would measure how many particles they got on the other side of the beam. In this picture, we had a theoretical prediction. I mean, we see a particle on one side, it means a quark was coming out. There was a quark on the other side. You can calculate how many hadrons it ought to make. And we came out 3 times too many. It was quite serious. We had found that the actual particles coming out have, on the average, a lower momentum than we expected. And in addition, I'm awfully sorry, but I didn't prepare it very well. I had some slides that I brought, but I haven't to show them. I forgot to put them in the pile. But the idea is also, if a quark is coming out which has a flavor, let's say a U quark, then the particles which are made, such as the mesons, would be more likely positive than negative. And so we also predicted a ratio of pluses to minuses that was different than 1. They were very different. And 2 things were wrong. There weren't enough of them, and the ratio of plus to minuses was about 1. It wasn't as big, more pluses than minuses as we expected. So therefore, this was wrong. Okay? So last time when I talked here, this experiment hadn't been done, so I was very enthusiastic about how things were working. Again, I'm enthusiastic because the experiment that shows that this isn't right hasn't been done. Okay, now, during all this time, there was developed, in fact, from the very earliest times, a theory, more specifically, a more specific theory of how the quarks interacted by exchange of a gluon, and that theory is now called quantum chromodynamics. And it represents our best attempt at the theory underlying the hadronic strong interactions, okay? I remind you to start with we start to discuss the character of the quarks in this theory of quantum chromodynamics. They have a spin a half and flavors for mysterious reasons. I mean, you just assume that, and masses, and assume that. Those are supposed to be some of the parameters of the theory. But in a thing like delta plus plus of spin 3 halves, we had supposed that there were 3 U quarks all spinning the same way, all in the same state, S state. And it was supposed to be true that particles of spin a half are supposed to obey a thing called Fermi statistics, no 2 particles in the same state. Or more precisely, the wave function must be anti-symmetrical for the exchange of the particle. Same thing. You can't have 3 particles in the same state, so these quarks were very peculiar. Well, some people said, well, they're peculiar, and they have this funny new property, unlike ordinary fermions. That is, particles of spin a half. It's called the exclusion principle, and it's supposed to work. It works for electrons, and it was supposed to be proved. Another school of thought says, well, maybe we did prove it correctly, and that these are not all in the same state. There's only one way out. If that's the case, that there are 3 different kinds, that these 3 quarks that we all thought were the same were not the same. And therefore, we suppose something to the flavor idea for each flavor quark, for instance, a U quark. Each one of them must come in 3 varieties, which are called colors, which we call red, blue, and green. So you see that there is a red U quark, and a blue U quark, and a green U quark. I may have confused you with the colors that I was using for the flavors, U, D, and S, which were in the earlier slides, blue, green, and red. And the present slide, in which I'm using the colors to represent the idea of this extra property. And therefore, it may be confusing, but I point out that difference. So therefore, in these flavors, I didn't color them, you see. So we have flavor U, or D, or S, or C, or T, if it exists, or B, if it exists, are supposed to come always one of 3 kinds. 3 colors. And if the 3 different colors, otherwise they're identical in properties. I mean, they're the same. They have the same mass, same spin, same everything, and they're coupled exactly the same way, and everything is symmetric as it can be. And then, of course, the trick is that you put three quarks together. What happens is that you can have the three different colors together. When you put a quark and an anti-quark together, how we can put it together in a meson, you can imagine, among other possibilities, that you have a red and an anti-red, a blue and an anti-blue, and a green and an anti-green, equal amplitudes for each. That is a nice superposition in quantum mechanically, so you can't tell which you have. The idea is this. The problem was, why is it that the states that we see only involve three quarks or a quark and an anti-quark in the hadron, never four quark states or two quark states or one quark state, anything. Whatever the crazy law of force is, it must be some magical way in which it sort of saturates when there's just three quarks or when there's a quark and an anti-quark. And this theory is designed to do that. Let me explain the problem of the saturation. Suppose that the problem were not three quarks that we wanted to stop at, but at two. Suppose we wanted to explain why it is, if we had discovered that objects of two squarks always come together in a low energy when we can't, if we try to take three squarks together, it doesn't go. It's a high energy. The way you could do that would be to suppose that there's a strong binding like electricity, and that squarks come in two varieties, sort of plus and minuses. The opposites attract and it sticks together. And if you have one, the charge is, it's a lot of energy in the charge, say, a single charge. You try to put three, you've got that extra single charge, and so on. And the two would saturate. And all this is a game to do the same thing with three. It's easy with two, plus and minus cancel. But with three, you need a very complicated kind of magic to make it come out that when you're done with three, it comes out bound and with a quark and an anti-quark, but not other combinations. And the trick is to suppose that there are gluons which hold the quarks together, and that these are the analog. There's an analogy because we're very stupid and we do the same thing again as we saw before. Not so stupid because nature has a good imagination, but sometimes does the same trick again. The interaction between electrons is understood as the electrons come in and you exchange a photon, a virtual photon it is, and they come out again. So there's a picture like, if that'd be an electron, then there would be an exchange here in between of some kind of an object, which we would call a photon, which go back and forth. We're going to make exactly the same picture, but they're going to change the names. It'll be a quark and a quark interacting by exchanging a gluon. But in order to make the numbers come out right so that three hold together and so on, a magic game has been played to suppose that the quarks come in this three colors. First of all, by the way, the fundamental process is that the quark goes to a quark emitting a gluon. So on the other side, the quark can absorb it. So this is the fundamental process that you should look at. But you see, we're going to suppose now that these quarks exchange colors when they interact. That is, a red and a blue quark, for example, after they exchange a gluon, will be found as a blue and a red. And there's a kind of exchange forces which saturate. We're used to seeing how exchange forces saturate in molecules, and that's where the idea came from. So we imagine that the gluons, in more detail, carry colors in the following magic way. That when a quark that's red emits a certain kind of gluon, which I'll call the red anti-blue gluon, then it carries the red away and brings blue in. That's anti-blue. See, it's going away, and it brings blue in, so it's anti-blue. So, and leaves the quark as blue. When it arrives on the other side, it would take a blue quark, which could annihilate the anti-blueness of the gluon, and the redness of the gluon would come out in that quark, and then we would have exchanged colors. It turns out when you do make a system of exchanging colors like that, and add one other feature, that no gluon is coupled to the average color, to the average of red plus blue plus green. Then it comes out that three bind very well, and a quark and an anti-quark in this combination bind very well, and all the other states are much higher up. So it'll make it work. Although it takes a little arithmetic to see it, it's not very difficult, is it? So that turns out then we need 8 gluons. Well, it's only colors, right? I mean, they're all equivalent, but they're different colors. There's the red anti-blue and its antiparticle. which is the blue anti-red. And I was rushing near the end here and didn't draw that one. These little arrowheads are supposed to tell you whether it's a particle or an anti, you see. So there's the other one going the other way. If you could say the same picture, but looking at it that way, it's a blue anti-green, anti-red. I thought anti-red was green in the color theory, but that's another matter. That's not in this theory. Then you could have a red anti-green and a blue anti-green, and its opposite. That's 6 combinations. Or you could have something with the 2 colors in it. You could have red anti-blue, blue anti-blue, or red anti-red, or green anti-green, which sounds like 3. But we don't want anything to couple to average color. So if we had something that went red anti-red, it would, if you had something like red, blue, and green together, it would feel red, blue, and green together because it would feel the red one. And we want the red, blue, green combination not to interact anymore. See, this proton doesn't interact with another proton by gluons, but by much more complicated intermediate particles. So the trick is to make a superposition of states again, so that there's 2 kinds. For instance, one that interacts with a blue with a positive sign and interacts with red with a negative sign. I should have put arrows on there. It's got a blue and an anti-blue in it. So it should have had this kind of arrow. It just changes blue back to blue, leaves it alone with a plus sign. This one changes, it also has arrows on it, red back to red with a minus sign. So that if you have a red and a blue and a green object, when this combination comes, it interacts positively with the blue and negatively with the red, and net is nothing. The other combination, which would be red, blue, and green, would interact both the same amount with red and blue, but would interact -2 units of green, and that way balancing out to 0. In that way, there's no other possibilities left. Well, there are possibilities like red minus green, but those are linear combinations of the other things. Quantum mechanics is kind of fun, but there's no more possibilities. So there are 8 colored gluons, and this exchange theory explains all the qualitative effects. Now the question is, how does the theory stand? So I give a report on how the theory stands. All right? Okay. First you think, as soon as you got a nice theory, all those wonderful theoretical physicists, which are being paid all the time, will calculate the consequences of the theory and compare it to experiment to see whether it works. This is known as the tradition of physics. It turns out that the damn fools find this mathematics of this theory beautiful and elegant and wonderful with all the little exchanges and all the operators which take care of the colors and all that stuff which I've drawn here, but which are beautiful mathematically. And they can't solve the equation. It's a temporary situation, I'm sure. We're all working very hard, but we haven't really worked out anything completely carefully quantitatively, so that there is no number. Like the magnetic moment of a proton has been measured to 6 figures. All we got to do is calculate it from the theory and check it. That's the end. Then we know if the theory is right or wrong. But at the present time, we can't calculate anything correctly. I mean, with knowing what the error is in it. You know, you can always calculate. Lots of papers in which they estimate something, and they estimate something, and it's more or less right. And if it wasn't right, they wouldn't publish the paper, so you don't know whether it means anything or not. And when they're estimating and they don't have a limit of error, there's no argument that says, they say, let's suppose that the third term is bigger than the second. Okay. But what about the fourth? Well, we don't know. But if we did, but in other words, there's no calculation with understanding of its own error. And that's what I mean by it doesn't have to be accurate. It has to have some known accuracy. Okay. It is true that qualitatively, it's easy to argue that the QQQ state and the Q bar state are indeed the lowest states. The big problem is why the quarks don't come apart. We've explained that we can understand everything qualitatively if the force continues to rise as the particles separate. In electricity, it's not true when you exchange a gluon, a photon, that when you pull apart 2 charges, the force continuously rises. It peters out after a while, inverse square law, and the 2 things can come apart. Well, I wanted to explain, I forgot to explain, one complication that makes the equations interesting, mathematically beautifully interesting, and complicated, which is important and rather lovely. Let's say you take this particular gluon. It interacts with anything blue or red. But this gluon carries blueness or redness. And therefore, the theory is symmetrical and beautiful and useful only if we allow this gluon to interact with that gluon. So that would mean that in the pictures of possibilities that are involved, there's also the possibility that a gluon and a gluon combine to a gluon, if the colors are right. I didn't draw the colors in. Now that means that there are many more and more interesting and complicated combinations of diagrams and phenomena and so on to calculate, and I wanted to emphasize that. That does permit the possibility. It's so complicated that we haven't calculated it, and therefore we can't, and nobody has even qualitatively made a clear argument of why it is that as the quarks separate, the force grows. But the argument from electricity that it must fall does fail when you count all the interactions of the gluons with the gluon. We don't have any analog of photons interacting with photons. Photons are not charged. So we don't know whether this theory is going to give forces that keep rising with distances if you try to separate isolated quarks. It is, however, still considered possible that the theory gives that, but it's not clear how. So this is what I meant by low momentum there is that long distances is the reciprocal of low momentum because the one is a Fourier transform. Momentum is wavelength, is inverse distance. So long distance forces is low momentum interactions. So we have confinement for particles of low momentum. At high momentum, it has been shown that although the coupling is strong at low momentum, as the momentum rises, the effective coupling between when you go to calculate a scattering and effective cross-section should fall with energy logarithmically, only slowly, but it should fall. It's as if the electrical constant charge was falling logarithmically with the momentum of the collision. This has been explained, in fact, calculated from the theory. So this is explained as an approximation. Now this picture, therefore, is understood as an approximation. This picture I'm talking about is that a proton has parts in it which scale. If the coupling were to go to zero, the parts would scale perfectly. When high enough energy, it's a weak coupling, and this is a good approximation. But it's only correct within logarithms. This principle that this at high momentum, the coupling is small, is called asymptotic freedom. And we understand that. We don't understand that part. The next thing then is to say, what happens now with this theory with the energy to the 8th and pp collisions? That was the biggest evidence that something was wrong. And what I want to tell you now is about that. What happens now when we take this new theory and try to understand how it might be that the energy looks like it falls to the 8th? Well, first of all, I pointed out that the coupling fell with energy. So when you make that calculation and you didn't assume that, you got the energy to the 4th. But the coupling falls, so it falls a little faster. A logarithm, but a logarithm ain't much. And it corresponds over the energy range in which the experiments were done. They're only done on a limited finite range because of practical consideration. It falls like, it makes the 4 into perhaps 4.5 or 5. The next, I pointed out that this picture of scaling was only approximate. There were logarithms in there also. And those logarithms, it turns out, work in exactly the same direction. We found 3 or 4 effects of the same, all working in the same direction, each giving about a half a unit, a few logs, which amounts to about a half a power. And accumulating all this junk, we were able to get up to e to the minus 6, but that's only halfway. Well, the other thing is, though, we had to add another feature, which is that just a moment. The reason that scaling is only approximate can be put physically another way. The scaling is exact, you could say, but the process which you assumed to happen wasn't complete. There are other processes. We assume that 2 quarks hitting each other only meant 2 quarks, but it's also possible that they come out, that this quark coming out splits into a quark and a gluon. And when those things are added, it has the effect as if the scaling was violated. And the result of adding this junk to what we did before makes the thing go to e to the minus 6. Now we have to add another thing, and that is that there are direct gluon collisions. Say, for instance, as an example, between a quark in the one proton and a gluon in the other. There are also gluon-gluon collisions. But let's take this one as an example. When you add these to the quark-quark collisions, the total cross-section is increased. And you remember that I told you that not only was it e to the 8, but it was too big experimentally. Magic. When you add all the rest of the possibilities together with the gluons, the total cross-section gets much bigger and now fits roughly with the experiment. The experiment is no longer that much too big. Also, because the things, when you have a trigger on one side, the things that come out on the other side might be gluons and turn out very often are, and not quarks, and gluons are colorless, have no charge, and so on, neutral, I mean. They have just as much chance of making a plus as a minus, and explain why the charge ratios on that away side were more like 1-to-1 instead of what we thought they were going to be. And further, if we suppose that a gluon, when it turns into hadrons, turns into somewhat softer hadrons than a quark does, we add that idea, then we can understand why the number of particles at a given energy on the away side was much fewer than expected. So we got all the puzzles explained, except we're only up to e to the 6th. In the meantime, the K perpendicular has been measured indirectly by an experiment. That is, the transverse momenta of the quarks has been measured. I'll only illustrate the results of the experiment by looking at pairs of mu's, which are produced by proton-proton collisions, which is supposed to be an annihilation of a quark and an antiquark. At any rate, by looking at the sideways momentum, two protons come together and something in there makes a pair of mu's, and you measure the two muons and measure the total sideways momentum. That measures the sideways momentum in the quark. And we found a distribution which was much fatter. It was a wide distribution, which was about twice as wide as we thought it was going to be. And so therefore, the transverse momentum inside, that sideways K perpendicular that I explained before, was larger than we thought. And we put that in, it makes a big effect, because you remember how when we had a high momentum on one side, if they had a transverse momentum inside, a good deal of it could be due to the transverse momentum. And that changes the prediction. It doesn't change the predictions if the energy were really very, very high. But the experiment's all done at a finite energy, and it turns out at the energy that they're done, it makes a lot of difference to the predictions. So we started all over again with the model, and we used quantum chromodynamics to include the logarithms, the shifting and the scaling, the larger transverse momentum, and so on. And I got this organized. Yes, I got this organized at the very end. I lost the transparency. And everybody laughs, and the lecture is lots of fun, and the lecture is confused, and still can't solve the problem, and now it's got it. Here is the curve in which we multiply by p to the 8th, and here's what the predictions are when we include all of the features that we know about from this theory. And in this has an advantage. The other theory, which showed the constant would now be an accident, of course. At very, very high momentum, the transverse momentum effects would be less and less important, so that the thing would start to rise, because I multiplied by p to the 8th. If the real thing went as p to the 4th, the curves will rise. So that's why they're rising out here. It's interesting that the absolute sizes of these curves are absolutely predicted by the constants from the quantum chromodynamics theory. So the quantum chromodynamics theory not only explains also, can explain, because it's still qualitative. We still have to put a few jiggles in to make it work. Unknown functions that we like, the distribution of gluons in the proton, we don't know. We have to assume something about how gluons turn into hadrons when they try to come out, because they carry colors and they can't be free. They have to turn into hadrons. Then we have to make some assumptions. But the point is, we can make reasonable assumptions and make everything look like it fits. There's no more mystery about this e to the minus 8th. It doesn't mean that the quantum chromodynamics has to be wrong. It could be right. And if it could be right, it is right, because it's such a beautiful theory. It's so natural looking, so on. It's obvious what to do. The most simple way to find out whether it's right, the simple way, is they do experiments at higher energy, and they're making machines which will take a couple of years, which will have higher energy, and in a minute they'll be able to tell whether they're right. In the meantime, they have all these other experiments already done. The theoretical physicists shouldn't be slackers. It's their job to calculate these things more accurately, from the theory, from quantum chromodynamics, with more precision, so that we can tell whether this deviation, for instance, here, from here to here, is a demonstration that something's wrong, or that we're right, okay? Furthermore, there were some functions that we didn't know that we had to adjust. Can we decrease the uncertainties by making a more careful theoretical analysis? And so I expect in the next year to be able to come back here and tell you that we have now been able to calculate the quantum chromodynamics, at least at the high energy end, where the couplings apparently get weaker, with sufficient accuracy to really test the thing quantitatively against hadron experiments like this, and have found that it is in fact, well, we'll wait till next year to find out. Okay? I have to answer questions now, they tell me. It wasn't hard if there aren't any questions. What? Well, I could, but it would take a little time. I'll summarize it by saying that we have quarks inside of hadrons. The hadrons are made out of quarks. The quarks come in a number of flavors. The different kinds of flavors give different charges and different masses to the quarks. We don't know where the masses originate or the flavors or what the number of flavors is. The question, however, is what holds the quarks together inside hadrons? And the theory is made by analogy to electrodynamics. There's exchange of a thing analogous to the photon, which we call a gluon. Then there's some complications about color, which makes the theory explain a few of the qualitative facts, why it's three quarks that go inside of a proton, and that's stable, and so on. And early arguments from hadron experiments which indicated that such a theory could not be right because cross-sections were falling too rapidly with energy, have turned out that that argument is false, and that it turned out that although we thought the energies were very high, they weren't high enough that this asymptotic behavior at very high energy, inversely as energy to the fourth, would or should have appeared at the energy range we see. But the very theory that we are hoping is right for the interaction of quarks inside of hadron is now got a new lease on life because it's possible, because it itself gives effects that look like P to the energy to the -8 over the range in which the experiments were done, or at least they could. But at the present time, the theory is not developed theoretically very far, and what ought to be done next, of course, is to do experiments at higher energy, but theoretically is to analyze this theory and to get going on solving these equations. The equations are all known, everything's finished, but we haven't solved anything. That's just, hey, I went over it again for you. Is there another question? Yes, sir. Yes. No, it will ultimately have a great deal to say about forces between hadrons. I guess I'm allowed to write, yes, right on here. A hadron would have, say, 3 quarks in it, which I'll draw quickly like that without taking out a different pen for each of the colors. But what can happen? You see, and they're held together by gluons. Well, let's indicate the gluons with a red thing. It's just like electrons held. These are gluons holding the thing together. Oh, all right, I'm using the wrong colors. I used red for, start over again. Here are the 3 quarks inside of a proton coming along. There's another proton over here. You'd want to talk about the interaction. Let's say a proton and a neutron in a nucleus, for instance. And these quarks are held together by these gluons going back and forth and maybe interacting with themselves and so on. It's all knotted up. So there's this little ball of junk, which we call a proton, which has these things going inside. Over here, it's also true that these things are interacting like that. These do not interact by simply one gluon going across here and these things coming out this way. This picture that I'm indicating here is not correct. And that's what, because as you said, neutral is not, if this gluon tries to come out of here, it comes out plus, -2 and it cancels, or whatever way it cancels out. And so what color have I got? Green, yeah. So that picture that I now drawn is wrong. But what is right and what is possible is the following. By the way, if this did happen, the forces would be much bigger than they are. But another more complicated thing can happen according to the theory, for which I guess I'll draw another picture, which is the correct picture. Well, we think so. These two go like that, and the quark works its way around. Well, it would exchange. I made a mistake. It exchanges a quark, or rather exchanges a pair of quarks. which is a more complicated operation. And these are all held together, held together, held together, held together, held, glue, 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 all over the place. Huh? But the method by which things interact, that is, the presence of one affects the motion of the other, is because more complicated things are exchanged. It's somewhat analogous to a sort of chemistry in which you exchange not a photon between atoms to get the interaction, but electrons themselves can be exchanged between two molecules and makes a covalent force and stuff like that. It's not directly, atoms are neutral, nevertheless they hold together. Okay, this is analog. Yes? Exactly, because a pion is a quark and an antiquark. If I had drawn this thing at a slight tilt in time, let's see, this is time that way, and if this was tilted a little bit, well, let's change the axis. Time is this way, so it's, I got a crank somewhere? Yes, I got a crank somewhere. Yep, good. Anyway, you see, this is a quark going forward, this is a quark going forward. This one is a quark, all right, but it's going backwards in time, and that's what we call an antiparticle. It's a particle going backwards. Because if you have a situation like that, you have a quark going along, and then it's going backwards in another quark. Then what happens is you have a quark, all of a sudden you have two things, one of which is a quark, and then you don't have, one of them disappears. Well, this is pair creation of a quark, antiquark, and pair annihilation. So the backwards end of that is an antiquark. So what you see going across is a quark and an antiquark held together by a gluon, but that's a pion. And so that's the way it is. So that this could also have emitted that little lump of quark and antiquark just goes sailing off as a pion. And it's indirect, and as you see, complicated. And one of the reasons why at this level we are still not able to compute things. It's like asking the early quantum mechanics to calculate the force between two molecules. Two atoms hasn't been done well yet. But there ought to be some elementary processes analogous to the hydrogen atom of quantum mechanics that we ought to be able to calculate. And I think that it's the high energy phenomena that are simple and that the theory will first get its teeth in accurately. And that's why I'm enthusiastic for this end of the analysis. Yes, sir. The color theory doesn't tell us anything about the flavors. You can have any, unfortunately, the theory is incomplete there. It only says what it is that holds the quarks together. It doesn't say how many different kinds of flavors there are. It would be analogous to the case of electrodynamics, in which, in the beginning, it was invented to represent the interaction of electrons, but then muons were found, or other charged particles, and the same damn photons are coupled to other things. It doesn't, the theory of electricity tells us there can be charged particles, but it never tells us how many there are or what masses. In the same way, we picture, the theory of quantum chromodynamics tells us there can be quarks. They have colors and so on. The color is just a way of talking about a funny kind of charge that's a kind of operator instead of a number. It's an operator charge, if you want, mathematically, but it's equivalent to this color picture. But what kinds of quarks there are? Any kind of quark has to have these colors, if it's a quark. But what kinds there are, that's we don't know. And so far we found 4. The value, the mystery continues. Why is the electrical charge of 2 of them plus 2/3 and the other 2 minus 1/3? Why are the masses of 2 of them, one of minus 1/3 and the other of plus 1/3? Well, since you're not familiar with these, if I show you this, it'll help. I can't. Oh, you got another crank. All right, good. Here are our quarks. It's very mysterious that these two are the charges are only these 2 possibilities so far. These 2 are the same mass, and nice and symmetrical. You have another pair, minus 1/3 and plus 2/3. Electrically symmetrical, but mass entirely different. How do you finish this picture so it's symmetrical? Oh, there's lots of wonderful ways. Why not put, what can we do? We can put, the hell with it. You put T's and B's and you invent some kind of symmetrical way trying to make it look easier. But I have to explain definitely that this theory that I'm talking about will, at the present time, has no understanding whatever of how many flavors, which ones are equivalent to what their charges are, or what their masses are. The idea is that the strong interaction is supposed to be explained. The interaction between what? That's to come from the next generation theory. Okay? And we do not have any existence theories that tell us what has to be about the colors, the flavors. Yes, sir? Well, that would take me some distance away. There is no, at the present time, was it considered, that, of course it's obvious, that the strong interactions are not weak interactions, nor electrical. And therefore, these colored gluons are not the weak interaction, or electrodynamic. But once one gets a theory that looks good, like the color interactions, one tries it in another realm. Maybe the weak interactions are another set of colors or something. So these theories are sometimes called gauge theories or Yang-Mills theories this time. And so they try Yang-Mills theories modified in such a way as to explain the phenomena of weak interaction. But those have not been brought to a general consensus of what is the right equations to try, okay? And there are theories which are trying to unify the whole thing and so on. But I'm a more pedestrian. I like to establish at least one part of the thing before I unify it all. It hasn't been done. Well, then you get other results. If, for instance, you had 4 colors, then the lowest state would be something which would contain 4 quarks. And if the quark flavors and charges are the ones that we propose, we would get a completely different spectrum of hadrons. I started in the beginning by showing you certain triangles of patterns, and those are experimental patterns of observed particles. These patterns would be different. The triangle would have 4 on the side instead of, 5 instead of 4. Huh? Yes, that's right. Yes, that comes out the same way. Yeah. Because what happens is this. They all must go into the same state, and therefore they must all go into different states of color. The color was invented, if you will, to explain why all these objects look like in every other respect they're in the same state. In some respect they must be different. Those are the colors. If you made it 4, it would come out 4. 4 could go into the same state, not just 3. And it changes entirely. The pattern of charges, of masses, and everything else looks entirely different. So the 3 of anything, that's the rightest. Those are the qualitative features of the theory that work. Yes? Well, that's why I didn't write them down. I can write them down, but it's just a bunch of symbols, and I explained them in writing these pictures by saying what things couple to what. One feature, I don't know, the trouble is, the reason I hesitate is there's 100 notations. Every time you have a new theory, then somebody invents a symbol that defines a certain way to simplify those equations. And I can write them very beautifully in simple thing. It won't mean anything because the definitions of the symbols requires a long description. But I think a qualitative understanding is just as good. But let me just explain part of the interest in complication. First of all, the coupling constant in the region of interest is large. The electrodynamics is easy to solve because the coupling constant is 1 over 137. And we use what we call perturbation theory. In making these diagrams, if there's only 1 photon exchangeable, that gives you a good approximation. If you have 2 photons exchanged, it's only a 1% or less correction. And so we can calculate the magnetic moment of a muon by this theory of electrodynamic, which muons don't involve quarks or strong interactions or anything. Only electrodynamic. And we can calculate that to 1 part in 10 to the 9th by calculating up to the order alpha, coupling constant squared to the 3rd or 4th power. And measured it, by the way, that accurately, and it checks. And that's why I said everything's all right with electricity. This theory has a much stronger coupling, and we can't make this series of terms. The 3rd one is as big as the 2nd one for protons. When you get to high energy, there is a hope. I mean, it's definite. It ought to be true that the coupling effectively is low enough that this perturbation method of analysis will work. It's only getting the logistics straightened out. What I mean by logistics is the actual phenomenon and observations involve real pions and real protons, which somewhere involves the strong interactions of low momentum, ultimately. you can do the high momentum part, but how do you glue the part you can do to the part you can't do in order to make a prediction of something that you can check experimentally without having to say, well, the part I don't do might obscure my result, so this experiment is unpredictable. You have to get the right combination of thing to measure, total number of somethings that you can really calculate, and the calculation is insensitive to the mysteries at low momentum, and it's a logistics problem. The high momentum is, I believe, nothing but perturbation theory again, and it's a question of clever logistics to extract it neatly from mix-up with the low difficult part, which is the low momentum end. The character of the theory that's interesting is, if you would wish, it's a field theory like electrodynamics, and it has equations like Maxwell's equations, very analogous, with vector potentials and scalar. You know, if you got differentials of the potentials or fields is equal to the charge densities and stuff like that. The charge density is replaced by color densities of the quarks. The differential equations in terms of potentials look the same with one important difference: they're nonlinear. Because they're nonlinear says that two gluons can make another gluon, and that's just a way of referring to nonlinearity. If the electrodynamics is not in a nonlinear medium, for example, it just means two photons can make another photon. That's not true in a vacuum. And so, but in the vacuum, it's still true. And so nonlinear equations are harder than linear equations. Not in perturbation theory, but when the couplings are strong. So we're behind the 8 ball in making sure predictions, even the qualitative predictions at low momentum. Yes, sir.
Does anybody look at the possibility of
Yes, people had looked for a while, but they couldn't find a neat patching that was sensible enough, that wasn't artificial and hockey looking and crude. And this thing seemed so neat and fixed it up that they've given up temporarily. If this doesn't work and something else turns out to be wrong with it, of course, we'll all go back to the drawing boards and remember all the dumb things we thought of that we have now rejected in favor of this most likely candidate, which I think is most likely indeed. It looks very good so far. I used to be more skeptical. Last year, I was skeptical because of these effects. This year, I'm a convert. Next year, we'll see. Yes? Well, it depends. It depends on what you're able to prove. If you're able to prove from the present theory of quantum chromodynamics that the force should increase all the time and the quarks can't get separated, and if the experiment that finds that the isolated quarks exist was really correct and checked and verified, which it has not been, and we do not know really that they can be separated, then it's an embarrassment. It would mean definitely that there's something wrong with the theory. If, on the other hand, careful analysis would only show that the quarks can be separated, and the experiment agreed that they are separated, there's no embarrassment at all, but a triumph, okay? So it depends on first checking the experiment and second checking, well, hasn't checking yet, because making sure of the derivation one way or the other of this theory. The point I try to make is that the theory is completely definite. Everything has been written down. There's only one constant in it, coupling constant, analogous to electrical coupling constant. And there's no freedom in the theory. There's a freedom of what flavors you put in, what masses, what charges for the quark. But there's no freedom for the part of the theory of interaction. This is not a usual situation. Under such circumstances, we're always very quick in checking and showing it's right or wrong. But at the present time, it's taken 4 years of playing around, and we can't even tell if this theory confines quarks, okay? But there's no question that either does or it doesn't. There's not a question that you can adjust something, okay? So whether it's embarrassing or not requires the experiment on the one hand and the theory on the other hand, both to be done well, neither of which. Yes, sir. Yes, sir. There are not supposed to be any free quarks. According to the present theory that I've described here about the quarks, nothing. This is not the only theory that's been invented about quarks and their interactions or whatever it is that holds hadrons together and the strong interactions. There are many theories, and over the 4 years, because of various difficulties in question, many alternative things have been thought of. Among others, is the possibility that the quarks were magnetic poles, monopoles, and that somehow was supposed to explain something. I never understood it myself, how it was supposed to work, but that doesn't mean that it was wrong. It just means I didn't understand it, okay? So I cannot make any criticism. I am prejudiced at the present time to thinking that this particular theory, which I've explained to you, which is quantum chromodynamics, is by all odds the most likely thing and the thing that ought to be followed up. If it gets into trouble quantitatively, okay, I'll turn back to all kinds of things, including monopoles if necessary. But at the present time, we haven't any need for that theory, which was not very definite. It was not a complete quantitative definite thing that you could expect to be sure to calculate something from. It was a suggestion as to what might be happening. Okay? It's one that I think that Professor Schwinger analyzed to a great extent. I don't know how he finally came out. Yes? No, they're not. They're supposed to be just as hard to get. Anything that has a net color is supposed to be inseparable. That color force, like electric force would be, always rises with distance. So in order to pull something which has a net color away from something else, which would have therefore a net color, if you started with white or no net color, the average charge 0, average color 0. And you pull something out that had average color, what's left behind has average color. And this would, we expect, produce very high forces which make pairs and the colors all neutralize and you get hadron. That's the present view. That would be just as true of diquark states, 2 quark states, as it is of a single quark, or 4 quark states. Only 3 can make no color, while a quark and an antiquark can make no color. 6 can also make no color. It's easy, 2 3s, each of which is neutral. But the guess is that when you have 6 making no color, it simply falls apart. I mean, the energy is low. It can fall apart into 2 3s, which are still interacting a little bit, and that's a deuteron. In other words, if the 3 is low, the 6 is not really held together well, and just comes apart into 2 3s, and that we understand their interaction indirectly this way. And that's the way we think we've closed the scheme. Is there another question? Well, let me come back next year. I enjoy this very much.